Ocho. Vos, ojo que está.
Buenas tardes a todos. Estamos esperando que entre el conferencista. Mientras tanto, les comento que esta charla, esta entrevista, forma parte de una serie de charlas que ha tenido en UNSAM, justamente, precisamente por los 100 años, este año que es el año de los 100 años de la mecánica cuántica, de la primera formulación de la mecánica cuántica. Hoy tenemos, hoy tenemos a Carlo Rovelli y dentro de 15 días tendremos a Paz. Ya lo vamos a anunciar.
Acabo de hablar con él, ya se conecta.
Perfecto.
Hablé directamente a su teléfono. Yo creo que se iba a conectar dentro de una hora porque hizo mal el cálculo. Los problemas que tienen los físicos con el tiempo en particular.
Y este en particular con el tiempo, ¿no?
Sí.
Y este con el tiempo en particular, claro, tiene, con esta cuestión lineal que tenemos nosotros con el tiempo, non c'entra niente questa forma del tiempo, digamos, ¿no? Ya se conecta.
Sí, está bien. Mario, técnicamente lo recibís vos, decís lo que te. Ahí está, ya lo conecto, ¿eh?
Bien. Si yo lo presento, Carlos, cuento alguna cosa de lo que hizo con la
Ciao
UNSAM.
Carlo, benvenuto. Benvenuto.
Eccomi.
Buonasera, Carlos.
Oi, I'm sorry for the hello. Hola. I'm sorry for the delay. I miscalculated the time. I thought it was 8 o'clock here in Spain, but here is 7 o'clock. So something has changed. Apologies. I'm here.
Okay.
Bueno, buenas tardes a todos. Tenemos el honor hoy de recibir en este ciclo que ideó nuestra querida vicerrectora y nuestro Aníbal Gatone, Ana María Lois y Aníbal, que se llama 100 años de la mecánica cuántica, a Carlo Rovelli, que es un conocido de la Universidad de San Martín. Digo un conocido porque participó, entre otras cosas, de un evento que hicimos durante muchos años, que todavía seguimos haciendo, que se llama Narrativa de lo Real, muy poco tiempo después de que se publicara un texto muy importante de Carlo, un texto no científico, sino de comunicación pública de la ciencia, que se llama, seguramente ustedes lo conocen, 7 breves lecciones de física. Los presento para los que no conocen un poco la trayectoria de Carlos. Carlos es un físico teórico. Bueno, es conocido por su trabajo sobre lo que se llama gravedad cuántica de bucles, y tiene obviamente bueno, todo su trabajo está vinculado a relacionar la teoría cuántica con la física einsteiniana y tiene obviamente una de las versiones, uno de los intentos de esa relación a partir de una interpretación relacional de la teoría cuántica. Y la naturaleza del espacio y del tiempo, con él aprendimos, bueno, aprendimos que esa forma newtoniana que tenemos de pensar en el tiempo y en el espacio no están tan apegadas al descubrimiento que hizo Carlos con el conocimiento de la mecánica cuántica y por lo tanto los invito a todos a que lean el hermoso libro también, no solo para no expertos, sino también para físicos, que se llama Helgoland, que salió hace un poco tiempo en español. Bueno, Carlos nació en Italia, trabajó en los Estados Unidos, en Francia, en Canadá, también está trabajando en España, es miembro del Instituto Universitario de Francia, es profesor honorario de la Universidad Normal de Beijing, fue doctor honoris causa, es doctor honoris causa de la Universidad Nacional de San Martín, en Buenos Aires, de la Mont University en Bélgica, es miembro de la Academia Internacional de Filosofía de la Ciencia y participa en la Universidad de Aix-Marseille hace mucho tiempo, en la Rodman Institute of Philosophy, en la Western Ontario University, el Perimeter Institute en Canadá, y en la Fractal Faculty en la Santa Fe Institute for Complexity. Rovelli, bueno, obviamente escribió muchos libros, escribió sobre Aristóteles, escribió sobre Anaximandro, escribió durante la última década, sin ninguna duda, bestsellers. De hecho, 7 breves lecciones de física, vendió más de 2 millones de ejemplares, para su sorpresa y el de su editor. Fue traducido a muchos idiomas, 40. Y bueno, en esa línea de trabajos están un libro que continuó a 7 breves lecciones, que se llama El orden del tiempo, y Helgoland sobre la teoría cuántica. Yo quiero decir también que Rovelli es un intelectual, en el sentido antiguo, en el sentido en que Traverso es una especie en extinción, diríamos, ¿no? En el sentido de que es alguien que desde su pasión por el conocimiento y por su quehacer, que yo diría, cuando uno mira un poco las referencias autobiográficas que hay en los libros de Rovelli, entiende que él buscaba algo más que entender la física de Einstein, que buscaba quizás poéticamente poder comprender el mundo en el que vivimos, ¿no? Y por eso su vida académica está además matizada con un gran compromiso político. Con un compromiso político que inició de muy joven. Es una persona muy conocida y por lo tanto hace uso de ese conocimiento, de haber sido en el 2019 uno de los 100 mayores, pensadores más influyentes en el Global Thinkers de Foreign Policy, o de los 50 pensadores por la Prospective Magazine, pero en cualquier caso creo que él aprovecha eso para efectivamente hacer una intervención pública en el sentido, obviamente, de defensa de los valores que parecen cada vez más amenazados, de una sociedad democrática, de una vida en convivencia, etcétera, etcétera. Yo, para terminar la presentación de Carlo, quiero leer un breve párrafo del prólogo de Helgoland, que me parece que lo pinta muy bien. Dice Carlo: he escrito estas páginas en primer lugar para quienes no conocen la física cuántica y sienten curiosidad por comprender, hasta donde sea posible, qué es y qué implica. He intentado ser lo más conciso posible, dejando de lado todo detalle que no sea esencial para entender el corazón de la cuestión. He intentado ser lo más claro en torno a una teoría que está en el centro de la oscuridad de la ciencia. Tal vez, más que explicar cómo entender la mecánica cuántica, explico solo por qué es tan difícil de entender. Pero el libro está pensado también para los colegas, los científicos y filósofos, que cuanto más profundizan en las teorías, más perplejos se quedan, para proseguir el diálogo en curso sobre el significado de esta física asombrosa y avanzar hacia una perspectiva general. El libro contiene además numerosas notas destinadas a quienes ya conozcan bien la mecánica cuántica. El objetivo principal de mi investigación en física ha sido comprender la naturaleza cuántica del espacio y del tiempo, compaginar de forma coherente la teoría cuántica con los descubrimientos de Einstein sobre espacio y tiempo. Una advertencia, dice Carlo antes de empezar: el abismo de lo que no conocemos es siempre magnético y vertiginoso, pero tomar en serio la mecánica cuántica, reflexionar sobre sus implicaciones, es una experiencia casi psicodélica. Así que los dejo en esta exposición de Carlos, que se llama Inside the Black Hole, quizás un título que se parece bastante a esa experiencia psicodélica.
Muchas gracias, Mario. Muchas gracias a todos. Yo entiendo un poquito castellano, especialmente el argentino, que es por un italiano es más fácil que... Yo soy a Madrid, aquí a Buenos Aires entiendo todo el mundo, a Madrid no entiendo nada de cuando. But I'm going to speak English because my Spanish, my Castellano stops here. I'm not going to try to talk Spanish. Well, thank you very much for this invitation. I'm very happy, and I have a particular somehow Argentina and Buenos Aires are particularly near to my heart for many reasons. So it's always nice to appear. I would like much better to be there in person, but that's what we can do. I'm going to talk about black holes. Yes, quantum is aspect of black holes. I want to tell you what I've been thinking recently about that with many colleagues, because this is new things, and I think they're interesting because they're new, is exciting, but also because it involves an application of quantum theory which pushes it to the boundary of what we know about quantum theory, namely its application to space and time, and it shows I think the possibility that quantum theory gives us to understand the world. So this is about application of quantum mechanics to space and time, and in order to understand what happened to black holes. And the question addressed is the easiest question that one could imagine. We see black hole in the sky. I'm going to talk a little bit about black holes classically in classical mechanics in general relativity before going to the quantum aspect. We see them, and we literally see matter that sort of spirals around them, and then it's going to fall in the black hole. And we have no idea what happened to this matter later. So we know it crosses the horizon, goes inside, and then, well, current science answer is then we don't know. So that's a question. And a similar question, a related question, is that we have reason to believe that black holes evaporate. So left alone, a black hole, it's going to become smaller, 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 and then at some point become very small. And then what? We don't know. That is outside the domain of classical relativity or quantum mechanics without the quantum mechanics of space-time. So these are the questions that are open. And at the end, I will arrive at a suggestion of what is a possible way of checking these ideas experimentally. It's speculative, it's an idea, it's a recent physical review letter that I've written with some couple of colleagues, a Spanish friend of mine, Alejandro Perez, and Marius Christodoulou, who is from Cyprus. So it's what I'm going to describe brings together quantum mechanics, general relativity, and the possibility of testing these ideas. I have very few slides, very simple, nothing complicated, no calculations, but just a few images. So let me turn them on. Here it is, portion of screen. I think this should work. Allow. Do you see these slides?
Yes, we do.
We do.
Okay, so let me start just very simply by saying a few things about black holes. I'm setting the slide right here. So this is a picture of black hole, right? This is a very famous. We have seen these in front pages of many major newspapers all around the world. This was taken in a very complicated indirect way by a network of radio telescopes. This is one with Francesca, my friend, sort of jumping around happy. This is in South America. This is in the Atacama Desert, is the ALMA telescope. And with these machines, we actually take pictures of black holes. This is very interesting because for all my life, black holes have moved from a purely theoretical thing to something we see in the sky. When I studied at the university, my professor told me, and it was written in my textbook, actually, the textbook written by a great scientist, which is Steven Weinberg, Nobel Prize, one of the greatest scientists of the second half of last century. Both my textbook and my textbook and my teacher said, well, most likely black holes are only mathematical things. They're not really real things in the sky. And they had good reasons for saying that, but nevertheless, they were wrong. there are black holes. Or at least there are things in the sky that best explanation we have, it's black holes. Now, I'm saying this because it's going to be relevant for what I say next. But I also want to emphasize that nowadays we have all sorts of evidence that there are these things which at best we describe them as black holes. We have these pictures, we have gravitational waves emitted by black hole mergers, we have radio information about what matter moving around black holes, stars orbiting black holes. We have a lot of things. And because of all this, in the last decades, we got all convinced that these things out there are black holes. However, we actually observed black holes since much before realizing that we observed black holes. And here is the first radio antenna. So this is the grandfather of these things here. This is a radio antenna that Karl Jansky built in the 30s. Karl Jansky was a physicist, a young physicist, was hired by the Bell laboratories to just explore radio noise around us, which was interesting because, you know, Bell was interested in telephone and communication, radio communication, and we wanted to know what is the landscape of radio noise around. So he built this antenna, just pieces of iron, kept with this some pieces of wood together in some way, which could rotate. I don't know. You see the wheels here and the circle on which it can rotate, and explore the sky. And with that, he measured the noise, radio noise in the just around. The first big radio machine antenna built, and he was able to realize that a certain noise was, I don't know, a thunderstorm passing by, other things, and then he got immediately a strange signal, these bumps here, once every 24 hours. This is the antenna is rotating slowly, but he realized that if you keep the antenna fixed, every 24 hours it picks a signal. And so he thought immediately it came from the sun, but then he insisted and looked more carefully, and it was not 24 hours, actually. It was 23 hours and 50 and something minutes. So it was, its periodicity was short, a little bit shorter than a day, which made no sense, because nothing like that could be human, could be in the solar system. What has a periodicity just a little bit than a day? And of course, the solution is obvious for anybody who knows just a bit of astronomy, of Ptolemaic astronomy. The rotation of the stars around us, it's a bit shorter than the rotation of the Earth, of the sun, because the Earth rotates, which gives the rotation of the sky. But every year one misses one turn, if you want, because the Earth goes around the sun. So that means that signal was coming from the sky. And that was big news. So big news that came out on the New York Times. This is a page of the New York Times in 1933. New radio waves traced to the center of the Milky Way. Jansky it was pretty easy at that point, once he realized it came from the sky, to understand which direction the sky, and it came from the Sagittarius constellation, and in the Sagittarius there is the center of the galaxy. So the new radio waves trace it to the center of the Milky Way. And now we know that the responsible is this object here. It's precisely the object that we see so well with these telescopes here. So the big news in the 30s in the New York Times were about a black hole. Of course, nobody thought at the time that it was a black hole, in spite of the fact that it was 15 years that the Einstein equation had been written. In principle, a good scientist could have said just 1 + 1, Einstein equations, black holes, here they are. But nobody was so smart. It took a century, almost more than half a century before realizing that. At the time, all speculations, including aliens sending us signals, were tried. And for when I was studying, which was in the 70s, so half a century after this article in New York Times, still nobody had connected this strange signal from the sky to black holes. The reason I'm insisting on that, you will see it later. So anyway, nowadays in the constellation of Sagittarius, somewhere there, by looking very careful with this fantastic new radio telescope systems, we see these things here. Now, how do we know they're black holes? First of all, because these things have all the features and all the shape, all the things predicted by general relativity. Let me just mention one. What this image actually is, it's a optical effect due to the black hole. It's not, there's no donut there. This ring is not an actual ring. It's like a rainbow. It's a optical effect. What goes on is that there are there is matter all around the black hole, very hot, emitting radiation, light, all sort of stuff, plasma, and it emits light, and we see that light. But we see that light that comes from there to us, strongly affected by the strong, super strong gravitational field of the black hole. So light falls in the gravity of the black hole. And so we see light that comes toward us in two different ways. Let me just take this away for a moment. I'll bring it back. And if you can enlarge my image, you can maybe follow better. If you have a star and you have light all around, you can see the light directly from the emission to your eyes, or light that goes around the sky, the star, and come toward your eyes by orbiting around it. So if light orbits, if a light can orbit around the sky, there is a particular radius distance from which you can get the light toward your eyes from all over. From every point, light can go around and then come to you. So therefore, you see around the black hole a ring, which is all this deviated light coming from all over. You see it from wherever you look. If you look from right, you look from left, you from up and down, you always see a ring. That's the ring that we see. So that is what we expect to see theoretically, and what we see is the same thing, just out of focus, because the theory is always cleaner than reality. So that's the first feature of a black hole, which is particularly interest, is a strong effect. So let me now move closer to what I want to say, which is what happened inside the black hole. So imagine that we go toward the black hole. Let me just present it in this way. So imagine we fly in a starship toward this thing here. We go through this plasma. In the center here, there is a little disk, which is a black hole. And the picture is a bit smaller than this black area inside. And the first effect that we observe is a colossal time dilation. Now, the time dilation that we observe is the following. Let me try to illustrate it carefully. This time dilation is going to play a role in what is coming back in a moment. Time dilation doesn't mean that when we are there, we observe anything special. We don't observe anything special by going near the black hole. When we are near the black hole, life is normal. We just feel the strong gravitational pull of the black hole because it's a big mass. The point is that if we look back at Earth, we see everything going faster. And if somebody from Earth looks at us, we see us going, everything going much slower. So in other words, while a sort of common stationary time passes, things age much faster on Earth than on near the black hole. This is a picture of the little boy here that remained boy and then becomes older on Earth. So if we send signals from near the black hole, we see everything going super fast on Earth, and from Earth we see everything going super slow. And this effect increases the closer we have to the black hole, to the horizon. So when we're very, very close to the horizon, we see super fast things happening. If you want to know what's going to happen 10 million years in the future on Earth, it's very easy. Just go near a black hole, wait a little bit, you're going to see it. Okay. Point is that you cannot come back. Then when you go back to Earth, you're in the faraway future. That's time dilation. But of course, there's much more. And the interesting part is what happened when we cross the horizon. This is a guy who understood that we can cross the horizon, David Finkelstein, wonderful scientist, fascinated by general relativity, fascinated by quantum mechanics, one of the deep thinker, I think, of last generation. He's not with us anymore. I met him when he was this age of the picture. He's the one who understood, just by looking at general relativity, that you can actually go through the horizon and nothing happens, through a beautiful, very simple calculation that later convinced anybody. Now, suppose we enter the black hole. What is inside? Well, the most remarkable aspect of the inside is that space is profoundly distorted inside the black hole. And the best way, I think, to visualize what happened inside the black hole is to think that this is a geometry of space inside the black hole, meaning the horizon is a little circle here. This is for the two-dimensional picture of a three-dimensional situation. The horizon is small, relatively small, but the inside is huge, is colossal. So a black hole is it's a little sphere thing from the outside, and if you just believe in Euclidean geometry, you look at the sphere on the inside, you know the volume inside, okay? But you're wrong in physical terms, because the geometry of space is not necessarily Euclidean geometry. It's distorted. So inside the same area of the surface, the volume can be much, much larger, because space can be large inside. And that's a way of picturing the inside of a black hole. For those of you who are sufficiently expert in general relativity, this is a very convenient foliation of the inside. Is a choice of a time slice inside, which is very convenient. Is sort of the natural one inside. So inside there is this there's this long direction, very, very long direction, at the end of which, careful, there isn't a singularity like people sometimes mistakenly think. The singularity is not at the center of the black hole down there. What is at the center of the black hole down there is the star, the matter of the star that initially collapsed, forming the black hole, which is still there, okay? Even if the matter collapsed long, long ago. I'll come back to that again. And so if we fall inside, we find ourselves in this long tube. And this geometry inside is not static, is not stationary, is changing. So while outside the black hole, the geometry remains the same, unless something happens, matter falls or we arrive or whatever. By itself, the geometry just remains itself. Inside, the geometry keeps changing. And how it changes in two ways. First of all, this tube becomes longer and longer. And second, it becomes narrower and narrower. So as time passes, tempo without IE in Italian, the tip becomes more far away, and the radial direction shrink. That's the actual geometry of the inside of the black hole. Now, it shrinks until, in a relatively short time inside, it shrinks to a line. And that's a singularity. So the famous singularity inside the black hole is not at the center of the black hole, it is in the future. It's not somewhere, it's some time, it's at some time. It's like if you enter in a room, it's not the singularity is in some corner of the room or in the center is the room. It's like the ceiling is squashing you at some point. It's squashing everywhere. Okay, so the singularity is in the future, not in a position. That's very important. Now, let me now make a comment because it's a crucial comment. Everything I said so far is solid. Namely, it's very credible. Unless we are wrong in something, which is always possible because we're scientists, that's what is predicted by general relativity. Everything which I said so far is just classical general relativity. Classical general relativity, we have no reason to think it goes wrong, okay? Now what I'm going to say, it's outside what we know with strong confidence, because we go in uncharted territory, and the uncharted territory is this red region here. So when we approach the singularity, that's where quantum phenomena comes in. Now, to say that we expect the singularity is obviously wrong, because we expect quantum phenomena coming in. The singularity is predicted by the Einstein equations, but for sure, the Einstein equations are not good when we approach this region here, because for sure, quantum mechanics, or for sure, I mean, to the extent scientists are sure about something, all reasons we have to believe that quantum mechanics becomes crucial there. So that's where the interesting stuff happens, because that's where quantum mechanics comes in. And if we fall inside a black hole, time passes, we are deeper and deeper, but we never get to the tip where the original star still there. We go more and more in, but much faster the tube shrinks around us and we get to the quantum region. And what about this quantum region? And that's where my work, my life work in loop quantum gravity comes in. So the theory on which I worked all my life, loop quantum gravity, is a theory which is designed to describe what happens in these situations. And to describe what happened in this situation, one has to stop thinking that processes are processes in time and processes in space. Because what is being affected by quantum mechanics is the geometry itself of space and time. So the geometry becomes a quantum superposition of geometries, right? Like a particle spreads as a quantum superposition of different positions. We have a wave function of geometries, which up to now, it's irrelevant because it's concentrated on a single geometry, but at some point the geometry is spread. And there are three phenomena, which are characteristic of quantum mechanics. One is the spread, the second is probabilities, right? We don't compute what happened, but we compute probabilities of what may happen. And the third is discreteness. What characterizes mechanics, quantum mechanics is discreteness, right? Electromagnetic waves are photons when we look in the small, or more precisely, manifest themselves as photons. So there's a minimal size of things. There's a minimal energy in harmonic oscillator, or there's a minimum angular momentum in something that rotates. And in loop quantum gravity, one makes a specific calculation. There's a minimal, it's the same kind of calculation that give all these minima. So it's a spectral analysis of some self-adjoint operator in some Hilbert space. And if we study the geometrical quantities, and Einstein general relativity tells us the geometrical quantity are dynamical quantities. So they're quantum quantities, and therefore they're represented by operators in a Hilbert space. This can be written in loop quantum gravity. You study them, and we find that they have discrete spectrum. So the intuitive picture is that in the small, this is a structure of space-time. It has minimal structures beyond which nothing can go, and the mathematical loop quantum gravity is a description of these structures here. Which means that somehow up here in the red region, this long tube can never become a line, because a line is much smaller than the minimal scale. The minimal scale of quantum gravity has a scale, it's a Planck scale. 10 to the minus 33 centimeters, nothing can be smaller than that because of this discreteness, which is a spectral properties of the operator describing geometry. So what happens next? Because something happens. Well, once again, quantum mechanics is very, if we take it seriously, it's very simple. Tell us what happened. If you have a particle falling into a 1/x potential, the equation explodes and the particle goes to infinite acceleration falling down. You have a singularity. But if you have a wave packet, it just bounces back very easily. Okay. If you have an electron falling into a proton perfectly radially, or a spherical shell falling into a proton, classically you get a singularity. Quantum mechanically, it bounces back because it's an excited state. It gets to a minimum radius, the Bohr radius, and that's it. Nothing can happen. It's by conservation of energy, then it comes back. So the obvious thing to expect is that by going through a quantum transition, you can jump back. And that's actually what happens if you take the equations of loop quantum gravity and you try to compute this transition. Namely, you have a classical evolution, a sort of tunneling effect into another classical evolution. Like when you have a particle coming to a potential well, it can go the other side, which is to jump to another solution which classically was not accessible, but quantum mechanics is accessible. So you have a probability of jumping to the other side, and the calculations say that that's what happened sooner or later, meaning sooner or later before the singularity. Now, what is the other side? Well, it's very simple. It's a bounce, right? It's a bounce of the wave packet. So it's the same trajectory as before, just time reversed. And the time reversal of this shrinking and getting longer of the interior of a black hole is the interior of the hole enlarging and becoming shorter. And this is exactly a solution of Einstein equations, which is well known, and it's called a white hole. So the inside transition from a black hole to a white hole is possible quantum mechanically. One can compute the probability for it to happen, and it gives a picture of what can happen through the singularity of black hole. So this is a number of quantum mechanical typical phenomena, quantum jump, probability, discreteness, conspiring to tell us smoothly a passage through a region in which you don't have a well-defined space or a well-defined time. You have a probability transition from a space-time process to another space-time process. Now, the complicated part of the story, if we try to bring this together, is what happened on the horizon itself. Because the inside is pretty simple. So this black hole forms, this transition, a white hole forms. The outside is also simple because if you study general relativity, the outside of a black hole and the outside of a white hole are exactly the same geometry. So black hole and white hole are two things which are the same outside but different on the horizon itself, and different inside. This is the wonderful intuition of David Finkelstein. David Finkelstein realized that the title of his paper was breaking of time reversal invariance on the horizon. He realized that the same exterior of a black hole can be bounded by something which is a black hole horizon, namely an incoming, an outgoing null ray, something you can only enter, or equally something you can only exit. The outside is the same. This is not hard to understand why. If you just take Minkowski space and you cut an incoming light ray and an outcoming light ray, you have the same exterior, which is bounded by something you can only enter and something you can only exit. Here's the same. So this geometry can be written down explicitly with precise formula. I'm trying to give you the visual picture of it. The only hard thing to understand is what happened right at the bounds at the horizon. And a lot of calculations recently have focused on that particular region. It's a small region. The inside we understand, the outside is trivial. What happened on the horizon itself in jumping from one to the other. And what the calculation indicate, which is not surprising, after that, even if when we struggle with that, we struggle a lot, we got confused forever. But what the calculation indicate is that the actual the probability of this actual transition of the horizon is non-suppressed only when the horizon is very small. Now, what about if the horizon is not small? What's going to happen? Well, here it's where the evaporation of black holes come in. All black holes left alone, sooner or later, have an horizon, become smaller and smaller and smaller, and when it's sufficiently small, it can jump. And now you can say, wait a moment, it may take a very long time to for a black hole to evaporate. In fact, Hawking theory gives us exactly the time as a function of the mass for an isolated black hole to evaporate completely and become Planckian size. So basically get to zero, almost zero. The time is in natural unit the mass of the original black hole to the third power. So we know it exactly. This is a very long time, but if I fall inside, I get to the singularity in a short time. How do these things stay together? Well, that's the magic of general relativity. They perfectly stay together because, as I said, the closer you have to a black hole, the closer time goes slower for you compared to the time outside. So outside, the time can be very long, and this is not in contradiction at all with the fact that if I fall inside, I get this singularity in a short time. In fact, if I could stay on the horizon itself, I could get there in no time, right? Because the horizon is a null surface. So a clock wouldn't change. If I am very, very teeny bit outside the horizon, even if for an external long observer, it takes a very, very long time for the black hole to evaporate. If I stay very, very close to the horizon, it takes a very short time for a black hole to evaporate. So no problem for a short time inside. All right. So all this stays together well, but careful. The transition happened only when the black hole has become small. So that means that the black hole can be large, evaporate, but the white hole is small. In fact, very small. The horizon must be Planckian. And so it's not really a white hole. It's in fact, my collaborators sometimes complain with me and say, you shouldn't call it black hole, white hole, because it's really a quantum object, because the horizon is it's Planckian size. And if you look carefully at the geometry that the quantum theory implies this has to us, is not really a white hole, the geometry here. It's a white hole geometry inside, but not on the horizon itself, precisely because quantum mechanics stop the evaporation on an eigenstate of the area, a minimal energy. It's an eigenstate of the energy, but this is a black hole, energy is area. So it's an eigenstate of the area. And since it's an eigenstate of the area, the conjugate variable to the area, which is extrinsic curvature, is maximally spread. And since it's maximally spread, this is quantum mechanics again, it can be neither positive nor negative. But the extrinsic curvature of black hole has a sign, white hole has the opposite sign. Of course, it's time reversal of one another. Extrinsic curvature is odd under time reversal. So if it's something is maximally spread in positive and negative extrinsic curvature, is neither a black hole nor a white hole. It's a superposition of the two. So these things that the remnant that the black hole leaves at the end of the evaporation, which might live for a long time, it's actually a quantum, the horizon is actually a quantum superposition of a black hole horizon and a white hole horizon. And the geometry is fuzzy and strange on the horizon itself. It's classical, can be classical outside, it can be classical again inside. It's a big white hole that slowly emits whatever energetic information is remaining. But the black hole, but the horizon itself is quantum. So I find that quantum mechanics and general relativity talk to one another marvelously. Quantum mechanics seems doing all the right stuff to work well with general relativity to make things work. If this idea that quantum mechanics and general relativity are incompatible to one another, it's completely wrong. The two things matches perfectly in all the picture. So that's a picture. There is this jump, this quantum tunneling, and as I said, the entire process, if you fall inside, come out, is very short. So if you fall in, come out, is very short. But if you look from a distance, it's very long. Now, let me come to the most interesting aspect now of all this story, because there is a lot of speculation here. I mean, it's really the gravitational field obeying the equation that I'm using to calculate that, or can we test all that? Well, let's look at this remnant here. It has to be very long, because all the information, the famous information lost inside the black hole, has to come out from a very small surface. So necessarily, this is very, very long. We have estimate of that. And the more we study the phenomenon, the more this seems to be long-living, this object here. We thought it was the original mass of the black hole to the 4th power. Now within the 5th power, could be even longer than that. So we have a very, very long-living object here. And we know its mass, because the area of this thing is the smallest possible energy before Planck, before Minkowski space. And loop quantum gravity gives you the spectrum of the area, so tells you exactly what is the minimal area, the minimal non-vanishing area, which is not surprising of the order of the Planck mass. A Planck area, which for general relativity tell us, Planck area corresponds to a Planck mass for a black hole. But a Planck mass is a microgram, is a fraction of a microgram, right? It's 0.14 micrograms. So it's like the mass of a hair. So if this story is correct, there should be objects around which have the mass of a hair and only interact gravitationally. Which a posteriori, we fell into this idea through all this analysis of black hole, but a posteriori is completely reasonable, because quantum gravity is a quantum field theory with a mass scale, of course, the ratio of the Newton constant and the Planck constant, and it's a mass, if you put the right power of c, the speed of light in, and the mass is order of microgram. So obviously, most likely a nonlinear quantum field theory with a scale has some object at that scale. So here is a prediction. There is a black hole leaves remnants, which are particles at this scale here. If you go to the details, it's the order of 20 micrograms, 14 micrograms. There are some numerical details not clear, but is there. And this can be detected. This can be detected, and there is obvious suggestion here that this is one more possible candidate for dark matter, right? Perhaps the biggest, not theoretical, but observational mystery today is dark matter. We see these halos around galaxies, but sometimes are just like here, away from the galaxy. So we know that there is some stuff out there. The best description we have about this stuff out there is that it's powder, which only interact gravitationally. Well, I just gave you the possibility, quantum gravity gives the possibility of powder, things with the weight of my hair, 20 micrograms is the weight of my hair, which only interact gravitationally. So if, and there's big if here, in early cosmology, a lot of black hole were produced, or even before previous era, who knows? A lot of micro black hole evaporated them, and have give rise to these remnants. The remnants could be all around, and maybe that's what dark matter is, and maybe it's this particle predicted by low quantum gravity at that particular mass. My last physics review D paper, it's with this Argentina guy, Alejandro Perez. It's an idea of how to build a detector to that. It's not completely impossible. It's not outside, not too much outside, let's say, current technology. With quantum technology, quantum interference, you can detect the small things flying by with that mass. We know how much dark matter there is. So if all dark matter is these things, we have an estimate of how many of these things are flying by, and we might build detectors to catch them. It's not something can be done tomorrow. It's a project, but it's a possibility. I mean, if there are a number of if in this story, of course. If this is correct, if dark matter is actually these things, if black holes were formed, but at least we have a direction to look at to test this possibility. Of course, if we could detect one of these things flying by, it would be wonderful, because it would be an indication of what dark matter is and a validation of these ideas of how to bring quantum mechanics and general relativity in. I think that theoretically this is the best problem today in fundamental physics, quantum mechanics and general relativity, and I think that the way to put them together is to look concrete phenomena like this one, see what they could predict together, and test them. What we come out, it's a marvelous idea, because it's an actual theory that tells us about processes which are not moving in space, in time, which are not space, is space itself that becomes quantum. And yet, quantum mechanics has all the tools for describing these processes. We have transition amplitudes, Hilbert spaces, self-adjoint operators, spectra. The standard machinery of quantum mechanics work well here. So that's the picture I wanted to give you. Pretty excited about that. And let me stop here, and all sorts of questions or anything here.
Okay, Carlo, thank you very much. You
Very
look
nice
like a
talk.
kid excited because you got something in your hands that need to be discovered, and that is fascinating. We can take 2, 3, 4 questions at the most. I don't know if you have dinner yet. You're in Spain, so you don't eat early there. But
Yeah, in Spain, and here people have dinner at 10 o'clock, 11 o'clock in the night. I mean, Spaniards are crazy for me. Yes.
Okay, I need you to remove the share. I can do it myself, I think, so we can see you completely and see who raises his hand or her hand to ask any question. In the meantime, as people gather courage to ask you anything, you are an awesome figure here in Argentina, so I don't think very many people would dare to ask you anything. But since we are not shy,
Yeah.
I'm gonna ask you. I didn't quite get it. What is the signal that suppose that I have to put up a detector to detect this potential dark matter candidate? What is the signal I should be looking for?
Oh, it's very clean here. So let's suppose this is all right. So then dark matter is made by these little particles of microgram. Now, dark matter, we have good models of dark matter. The astronomers give us good models of dark matter. There's a big cloud which is around the galaxy and is not rotating. The galaxy is rotating. So the solar system is moving with respect to dark matter, which means that there is a wind of dark matter particles. We even know the direction from which it comes. And since it's cold, the dark matter, it's not moving very fast. So it's a relatively not too large angle from which it comes. So we have this particle coming by. They don't interact electromagnetically. They have no strong or weak interaction, but they interact gravitationally. So they pull stuff with Newton force. So you want a detector that detects very small momentum transfers. Yeah, it's a little pull. I mean, and you can do some calculation, and the best way to detect them is to use quantum interferometry. The theoretical idea: imagine you have a particle which is split in two, superposition of two particles. And one of these dark matter particle comes near one. So it gives a little kick to this one. So the phase changes. So now when you bring them together, there's interference between the two. And that's how you can detect it. And the best way, the best idea that came is to use Josephson junctions, which essentially is an electron, which is half here, half there. So when a particle comes by, there's a little tiny current that goes through. It's super sensitive. It's a super sensitive detector of whatever you touch the electron one side and not the other. There's a little current that goes through. So if we could take many of this Josephson function, fill this room with, okay, when a particle comes by, sorry?
No, we didn't interrupt.
Oh, okay, there was some interference. Then a particle goes by, so all these little currents can be captured, and we can reconstruct the particle flying by, the signal. We know the direction, and more importantly, we know the mass of this object, so we can compute exactly what is in its pull, its effect. The theory predicts a given specific mass. So if we could detect a particle coming, or a few particles coming from that direction with that mass, I mean, what else could it be?
Good,
Very
great.
nice, very nice.
Is there anyone wanting to ask Carlo a question? Please raise your hand. It seems that you you embarrass them all. It's anything you want?
No, I want to thank you very much for this nice talk. Actually, it was new for me topic.
Okay.
And I accept, really thank you for having accepted to talk with us today. And I guess I'm going to watch some of your other of your talks, which I don't read.
Thank you.
And I have already read your books.
Is to put out money and try to make this detector. I mean, it looks expensive compared to the ones that are in the so it's not that expensive.
No.
Well, I don't know how many Josephson junction I needed. Many probably.
Very many of them, yeah, but it's worth it. Okay.
Yeah. Yes. Well, less on LIGO or the CERN machine, I imagine.
That's good.
Much less expensive. So I hope somebody. I'm a theoretician, so I need experimentalists to start looking carefully at all the technical details of that.
If you have 1 minute, I always mean to ask you a simple question. I mean, you have a brain which is 1.3 kilos above your shoulders, the same as all of us. However, you train it, we train it as well. But you can see, I feel a little further. But my question is, your impression about what is out there, reality. I mean, I keep thinking of the dog that sits with me when I watch TV on my couch. Does he understand what a couch is? What his master is doing watching a TV screen? Is there any future in trying to sort out what the universe is made of? Or it's just a little game that we play because otherwise we don't have anything better to do?
I think that let me try to take. No, it's a beautiful question. Let me try to answer seriously. I think that we should not ask. I think that the question, what is sort of the ultimate reality? What is the actual final description of how things are? It's not a good question. I think it's a useless question. I think the way things are. Every object can be described in a variety of different ways, at different levels, and it's quantum mechanics itself that does tell us that we cannot go to the bottom. What we always have, it's a way an object influence something else. So we can learn more. We can always learn more. I don't think it's interesting to try to ask the final question. The more descriptions we have an object, the more complex things. The nature is infinitely complex. It's not that we don't know it. It's that I'm not even sure it makes sense to ask the question of how are things ultimately made. In a sense, you know, physics has failed repeatedly to the, to give the final picture. It's at some point it seemed like with Newton it's just particle with forces. No, that's wrong. It's also fields. Okay, that is fields that obeys equations. No, because there is quantum mechanics. Okay, the things evolve in time. No, because there is general relativity. So we never have a final story. Why don't we give up this idea of the final story? Every time we understand something better, we're happy because we understand something better. And so we have open questions because there are things we don't understand, we cannot predict. So I think it's more interesting to look at the open questions and try to fill gaps, thinking that there will be always new questions that are going to arrive. That's my take.
Okay. I appreciate your take on that. Mario, would you like to bid him farewell? ¿Te gustaría, Mario, decirle algo? Mario, are you there? No, I think not Mario.
No, sí,
He's reappearing.
No.
Ah, okay.
No, le condizioni per fare una domanda a te, Carlo, sulla fisica. Mi fa incoraggiare per leggere tutto quello che hai detto.
Ok,
Then,
ti diciamo addio, Anton.
Grazie di tutto.
thanks a lot again for being
Thank
with
you.
us.
Muchas gracias de todo.
And for sharing this new piece
Yeah.
of work with us.
Yeah.
Thank you very much.
Thank you. Very much.
Bye bye.
Bye.
Grazie, Carlo.
Thank you very much.
Ciao Mario.
Ciao.
Chao. Gracias a todos por haber participado de esta charla, este intercambio.
Gracias a ustedes por organizarlo.
Por haberlo ofrecido. Muchas gracias.
Hasta la próxima.
Hasta la próxima.
Hasta la próxima. Chao, chao.
Bueno, yo lo tengo.